Okay.
Oh, good afternoon, Jared. How are you?
Fine. And you?
I'm okay. How is Nairobi?
Not bad. It's excellent. Actually, today it's sunny.
Okay.
Yeah.
Maseno is warm.
Yep. Let's try if we can share the screen and.
Okay.
Yeah, and then I will. Think the host is not here, so but I'm fine.
Okay.
You're here. Yes.
Hope you're able to see my screen.
Yep. Yes, we are. Thank you. And full screen or something. You can try that. Just to make sure that. Great.
Yeah.
Yeah. So I think. Yeah. I think it's great. I'll try to play the anthem, and then we begin straight away. That I will do. Yeah.
Africa, sing now, Africa, sing loud, sing to the people. We'll ring the bells when you come back. We'll beat the drums when you come back. We'll ring the bells when you come back. We'll beat the drums when you come back. Our lost African music will turn into the music of the people. Here's the people's music, but the people's culture, and I'll be the one who'll climb up the mountain, reaching for the top of our Africa days. Africa sing, Africa sing, Africa sing, Africa sing, sing, sing Africa, sing, sing Africa, sing, sing Africa, sing, sing Africa. My boo, yeah, Africa.
Okay, thank you, colleagues, for coming this afternoon. So today is another day for the African Math Seminar, and we are extremely excited to have Dr. Isaac Owino Okoth from Maseno University, from the Department of Pure and Applied Mathematics, and is a faculty member there, and is the head of department actually in that university. So Isaac has a PhD from Stellenbosch University in 2015, and his thesis is around number combinatorial objects and actually enumerating them. So it's quite exciting that is with us today, and we look forward, Isaac, for your talk. Welcome, Isaac.
Thank you. Okay, so thank you, Jared, for the very nice introduction. And I also want to thank Professor Paul Vadelind of the Combinatorial Research Group. That's a research studio who actually suggested that I recommended me to give this talk in the African Mathematics Seminar. So I'm very grateful to Professor Paul. I knew of the African Mathematics Seminar through Professor Ogonji, who is here in Maseno, who is a mentor. So I'm very grateful, Prof, for informing me about the African Mathematics Seminar. So today I want to give a talk on what I do, the research, about the research I do here in Maseno. And the topic of my presentation is enumeration of k-noncrossing trees and related combinatorial structures. So that is my name, Isaac Owino, as you've been informed by Dr. Jared, and I work here in Maseno. So I'll first start by explaining what we mean by these trees, and then the kind of trees that we are interested in, and then we see what to enumerate. So a tree is a connected acyclic simple graph. What we mean by a simple graph, this is a graph which has no loops and no multiple edges, and as acyclic in the way that there is no cycles, and connected in the sense that you can get a path from a given vertex to another vertex. So there are various types of trees that have been studied. Some of them include Cayley trees, non-crossing trees, plain trees, DRE trees, just to mention a few. So here are some of the examples. So this is a Cayley tree. A Cayley tree is a labeled tree. So the vertices are labeled with integers in the set, maybe 1 all the way up to n. And a non-crossing tree is a tree drawn in the plane with vertices in the boundary of a circle such that edges are line segments that do not cross inside that circle. And plain trees, these are trees in which the children of the vertices are ordered. So it is known that Cayley trees are counted using the Cayley's formula, which is given here, n raised to power n minus 2. If the number of the vertices is n, then the non-crossing trees is given by this formula here, which is a generalized form of Catalan number. And plain trees on n vertices is given by the nth Catalan number. So if you have a collection of trees, then we'll call that a forest. Okay, so consider this plain tree here. So we'll say that this vertex x, y, z will be called the children of u, and they are going to be called siblings. So the parents of x, y, and z is this vertex u. So in a k-labeled tree, any two, that's in any tree, if you have any two siblings, a sibling that appears on the right, or in any plain tree that appears on the right, will be said to be a younger sibling, to be a younger sibling to the one that appears on the left. Like here, x is the oldest, followed by y, then followed by z. So z is the youngest among these vertices here, x, y, and z. And the number of children of any given vertex is said to be a degree. So the degree of vertex u here is therefore 3, because there are 3 children of that vertex u. And a vertex of degree 0 is a leaf. So x here is a leaf, y is a leaf, and z is a leaf. And a vertex which is not a leaf is called an internal vertex. So u here is an internal vertex. So a DRE tree is a plain tree, but with the condition that the maximum number of the children of any vertex is d. Like this graph we have here, or this plain tree we have here, the maximum degree of any vertex is 3. That's the root here has degree 3, and u also has degree 3. So we can call that a ternary tree or a theory tree. And if all the vertices have d children or 0, then we call it a complete DRE tree. So this fails to be a complete DRE tree. But if we could be having another edge here from this vertex, maybe coming down, then it could be a complete ternary tree. But the way it is not a complete ternary tree. So non-crossing trees have been generalized by combinatorial structures, which are called k-noncrossing trees. And these were introduced by Pang and Liu in 2010. Though the 2 non-crossing trees were earlier considered by Yang and Liu. That is, I think, in 2009. So we define a k-noncrossing tree, which is actually the objects of our enumeration today. So it is an uncrossing tree where each node receives label in this set, such that if you take the sum of labels along any ascent, then does not exceed k plus 1. That is if we consider the paths from the root. So I'll give an example of a 4 non-crossing tree. So this is a 4 non-crossing tree on 12 vertices. We are taking vertex 1 here to be the root. And it is labeled by 4. So it is the vertex 1, which is labeled by 4. So the subscripts are the labels we are giving to the vertices. And if you consider any ascent from the root, like from this vertex to vertex 6, and you try to sum the labels there, which is 4 and 1, that will give you 5. But 5 is actually the maximum you can get, because it's supposed to be less or equals to k plus 1, of which k here is 4. But note here that here you'll have 2, 4, then 3, 1. That also gives you a 5. But it is possible that it could be greater than 5 if it is not an ascent. Like this edge here, 2, 3 is, 3 to here is not an ascent because it starts from 3 to 2. If you consider path from the root, so it fails to be a root. So this condition is only satisfied for ascents. So Pang and Ulven obtained the formula that get you the number of k-noncrossing trees, and it is a general form of Catalan number if the number of the vertices is n and the root is labeled by k. So this same formula here counts 2k array trees, 2k plus 1 array trees if there are n minus 1 internal vertices. Okay, so non-crossing trees have been enumerated by many researchers, and the statistics of the enumeration have been number of vertices, number of endpoints, boundary edges. You can talk of a degree of a vertex, maximum degree of the root, descents, left and right leaves. All of these have been enumerated, but they have never been enumerated for k non-crossing trees. So in this talk, we will present our results on enumeration of k non-crossing trees according to root degree and forest. Then we will present some bijections which relate these trees to other combinatorial structures, which we will introduce along the way. So this result was first proved by Pang and Ulven, and it shows that there is a bijection between the set of k non-crossing trees on n vertices, such that the root is labeled by k, and also the set of complete 2k plus 1 array trees with n minus 1 internal vertices. So as I've said, that was first proved by Pang and Ulven, though I provided another proof based on an earlier proof of Yang and Liu, for which they constructed the bijection between the set of 2 non-crossing trees and 5 array trees. So I generalized their bijection to prove this theorem here. So it is observed that in a k non-crossing tree, if the root is k, then its correspondence to k plus 1 array tree with n minus 1 internal vertices is going to have a leftmost path of length d. And this result is there from lattice path enumeration, that if you want to consider the number of lattice paths with a unit up step and unit horizontal steps from this vertex here, ij, to this vertex here, so that they do not cross the line y is equals to mx. They can touch, but they don't cross, and they need to be below that line. Then it is given by this formula here. So if we set I here to be equals to 0, j is equals to 0, n equals to n minus 1, m equals to 2k, then you will find this formula here, which counts k non-crossing trees on n vertices of root. The root is labeled by k, by root labeled by k, and such kind of paths are called good paths, meaning that we can prove. Okay, so let's take this first, what we have just explained there, that there is a bijection between the set of complete 2k plus 1 array trees on n minus 1 internal nodes, and then with a set of good paths from the point 0, 0 to this point here, of which there is a unit horizontal step or a unit vertical step. So how do you prove that? So you traverse a complete 2 plus k array tree with n minus 1 internal vertices in pre-order. So we are going to traverse this in pre-order. Pre-order here means that you first traverse the root, visit the root, then you visit the leftmost subtree, then followed by the second, third, until you move to the last one. And then we are going to draw a horizontal step for each internal vertex, and we are going to draw a vertical step for each leaf. And we are going to do this except for the last leaf. And that will provide that proof, and the process you'll see can easily be reversed. So consider this. This is a 5-array tree. So we want to show that you can get a good path. So what you do is that you traverse this tree in pre-order. You start at the root here. So that for the root, you draw a horizontal step. Then you come down to the first internal vertex here, and since it is an internal vertex, you draw another horizontal path or step. Then the next one is this step, is this internal vertex, so you draw another horizontal step. Then you move here, you get a leaf. So for a leaf, you draw a vertical step. Then you are traversing in pre-order. So then we visit this vertex here, which is an internal vertex, so you draw a horizontal step. Then the next one is the leaf. So you draw an up step, then the leaf, 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 all these leaves. So those will give you the up steps. So you get to that. So it won't cross this line here, y is equals to 4x. Here, this is a complete 5-array tree, meaning that its correspondence k-noncrossing tree is going to be a 5. It's going to be a 2 non-crossing tree. So it's going to be a 2 non-crossing tree. So k there is 2. So that's why we get this is 4x. So the process can easily be reversed. So we get our first theorem that the number of k non-crossing trees on n vertices such that the root is labeled by k and the root is of degree d is given by this formula here. And the proof follows by the observation from here that if the degree of the tree is d, then there is going to be a path, leftmost path of length d in the d-array tree, in the k2 plus 1 tree, array tree. Like here, the leftmost path here has length 1, 2, 3. There are 3 edges on this path, meaning that its correspondence k non-crossing tree was of degree d. And the number of the horizontal path here at the beginning of this path is of length 4, meaning that the number of these trees of degree d should be, we should start enumerating, counting the number of paths from this point here, that is from d1 all the way to n-1, 2k, 2kn minus 2k, which that's what I've explained. Okay, so that proves this formula here, which is the first result. So next, we want to enumerate these trees according to the number of forests. You recall that a forest is just a collection of trees. So the trees, the forests we are going to consider here are going to have 2 properties. One is that each component is rooted at a vertex whose label is the smallest. And 2, the components are k non-crossing trees themselves, the root labeled by k, and that the components do not intersect each other. So we use generating functions to prove this theorem, that the number of the forest on n vertices, if there are r components of each component is a k non-crossing tree whose root is labeled by k, is given by this formula here. Note that if r is 1, then you just get a k non-crossing tree. Okay, so we construct the proof. So we'll let T to be a generating function of the components, that is of the k non-crossing tree, root labeled by k. Then we are going to decompose the forest according to the non-crossing tree rooted at vertex 1. So if the component that has m vertices, that's if the tree has m vertices, then we can decompose it this way. like this is the tree rooted at 1. So the number of vertices are m, or is m. So then you can have, here can be filled by forests, of which some can be empty. Meaning that if Tz is the generating function for the non-crossing tree, that is k non-crossing tree, and then we let f of zw to be the generating function for the forest. Here, z marks the number of the vertices, and w here marks the number of components. Then it is going to be given by this. Let me explain that. So it can either be empty, or you'll have the non-crossing tree, that's Tm, of which non-crossing tree, and you have the forest, the m of them. And if you compare this with that, so replacing z here with zfz of w, then you obtain this one here, meaning that the generating function for the forest can as well be written like this in terms of the generating function for the trees. So then we let tz here to be z into 1 plus uz. Then it is known that the functional equation for the generating functions of the 2k non-crossing trees, whose root is labeled by k, is given by this. This is in the paper of Pang and Levin. So using this, setting that t of z to be this, then u can be written in this form here. Okay, so then we can let fz of w to be 1 plus wy. This is for the ease of calculations. So that you have here 1 plus wy is going to be equals to that, because it is fz of w. So it's equals to this. So which reduces to y equals to tz 1 plus wy. So, but this is not in a form in which you can apply Lagrange inversion formula to extract the coefficients of what you want. So we define Q to be of this form. So to be of this form here, and since y is given by this, so z into 1 plus wy is going to be the t inverse of y. Then we'll have that z 1 plus ty, because what you have here, you can write it as y over q of y. So you write it in this form. Okay, so it follows that from here, that you can write y to be equals to this term here times qy. So times qy. And this is in a form you can apply Lagrange inversion formula. So we want to extract the coefficient of Zn because we want the number of vertices in our forest to be n. Then Wr, because the number of the components is r, of which W here was marking the number of components in this. So this is going to be given by, note that f of Zw was 1 plus y, Wy, meaning that if you want to get the coefficient of Wr in this, it's the same as getting the coefficient of W raised to power r minus 1 in y. So applying the Lagrange inversion formula, we get this. Again, here you use the binomial theorem to get you to this one here. So it remains to find the coefficient of this. So once we'll be able to get the coefficient of that, then that will have proved our result. And by definition, we know that t is equals to this, because actually t of q of t was t over t inverse of t. Okay, so writing t of z to be in this form, again, we had said you can write it in this form. Then we have t, which is this way, can be written like that. Or we can make q of t the subject. So we write it in this way, where u of z, as we had showed before, satisfies this condition here, or satisfies this equation. So from here, you find that q of t minus 1 gives you this result here. And we can use this, that is u of z equals to that, to write this part here to be this, which reduces, of course, to that. But still, it is not in a form you can apply Lagrange inversion. So what do? We set TQ of t raised to power 2k to be pt. So p of t is going to be this, that's from there, and that is going to be t. So this part here is the same as you are taking t here and you are replacing that with t raised to power 2k. So that gives you this, which reduces to that. So we have p of t equals to this, which is in a form you can apply Lagrange inversion formula. So what follows is just applying the Lagrange inversion formula to get you this. So that is the coefficient of t raised to power n minus r in this q of t raised to power n. So to get our formula for the number of forests on n vertices with r components, then we just replace that value, that coefficient of t raised to power n minus r in q of t raised to power n, which we obtain to be this, and the formula, and therefore everything reduces to this. So this formula here, therefore, is the number of k non-crossing trees on n vertices and r components. The root of each component is labeled by k. Okay, of course, if you substitute for k is equals to 1 here, then we get the number of forests. Yes, the number of forests of non-crossing trees obtained by Flageolet and Noy. And for you place for k is equals to 2, then you get the result for 2 non-crossing trees, the forest for 2 non-crossing trees. Okay, so these combinatorial structures, k non-crossing trees, they can be related to other combinatorial structures, which we are now going to look at. And I'll first explain what k-plane trees are. So if the vertices of the plane trees are labeled by integers in this set, such that the edges ij satisfy this condition here, which was also there for the non-crossing trees, k non-crossing trees, though it was only for the ascent, but here it is for all the vertices, then we obtain k-plane trees. And these trees were introduced and enumerated by Nancy Gu, Helmut Prodinger, and Stefan Wagner. So the number of k-plane trees whose roots are labeled by k is given by this formula here. So if we set k here is equals to 2, then we get 2 plane trees that were first studied by Nancy Gu and Helmut Prodinger. And sometime in 2010, Du and Yin enumerated k-lit trees whose edges are oriented from vertices of lower label towards vertices of higher label. Then they enumerated them according to in-degree and out-degree sequences. So they call them local trees. And this actually incited the subsequent work of Okoth and Wagner, in which they enumerated non-crossing trees, of which the edges were again locally oriented. So they called them locally oriented non-crossing trees. And in these trees, if the degree or the in-degree of a vertex is 0, that's the number of vertices which are oriented into a vertex is 0, then we refer to that as a source. Then if the out degree is 0, that's the number of edges that are oriented away from a given vertex is 0, then we call that a sink. Okay, so k non-crossing trees whose edges are locally oriented, we will refer to that as locally oriented k non-crossing trees, which actually I've studied that. And the non-crossing trees whose labels increase along paths, if you move from the root, were introduced by Asinovsky and Manso in 2008, and they call them non-crossing increasing trees. They are counted, of course, by the famous Catalan numbers. So the same idea could be extended to k non-crossing trees to get k non-crossing increasing trees. So I showed that they are enumerated by first Catalan number. And for the special case, k is equals to 2, I showed that they are counted by the same formula that counts plane trees. Okay, so this is also a result I proved that there is a bijection between the set of k plane trees on n vertices whose root is labeled by h and the set of k non-crossing increasing trees on n vertices whose root is again labeled by h. So we will require this to prove a result which we are going to prove later on. Okay, so if we compare the formula counting k-plane trees on n vertices with root labels by k, and the formula that counts the number of k-noncrossing trees on n vertices with root labeled by k, then you see that there is some relation. That is, if we replace k on this side here by 2k, then we obtain this formula, meaning that there should be a bijection between the set of 2k plane trees on n vertices whose roots are labeled by 2k and the set of locally oriented k non-crossing trees on n vertices whose roots are labeled by k. And this is a result that we obtained with one of my students, Albert Nyariaro, that there is a bijection between the set of 2k plane trees whose root is labeled by 2k on n vertices and the set of k non-crossing trees whose root is labeled by k. So the formula for these trees, if you orient the edges, is actually the same. So I'm going to give that bijection. So we can start with a 2k non-crossing, 2k plane tree, like this. Like for what we have here is a 4 plane tree. The root is labeled by 4, so it's a 4 plane tree. So from this 4 plane tree, we can turn it into a 4 non-crossing increasing tree. That is, you have this vertex 1, then these 2 vertices here, they are going to be connected to the root like that, and the edges are oriented. The trees are such a way that they are always moving to the right. That is, they are only the left butterflies. There are no right butterflies. So we have 1, 3, that's the 1, 3, then 1, 2, so there are these vertices, these vertices here, and then lastly the 4, 3 are actually the 4 and 3 here. So this tree here is what we called a non-crossing increasing tree. So since it is labeled with the vertices in the set 1 to all the way up to 4, so we call it a 4 non-crossing increasing tree. Okay, so to get a 2 non-crossing tree, so what we are going to do, you are going to look for the vertex, like here, this is a 4, so 2k. So 2k plane trees mean that these edges are labeled by the integers 1, 2, 3, 4, all the way up to 2k. So we are going to be interested in the vertices labeled k plus 1, k plus 2, k plus 3, all that. So we first look for a vertex labeled k plus 1. Like here, k is 2, so k plus 1 is 3. So you look for a vertex labeled by 3, which is this vertex here, vertex 4, is labeled by 3. The subscripts are the labels by 3. So what you do is that you delete this edge and you create an edge just before the vertex that was incident to this vertex. That's, you create an edge from this to another vertex just before it. Then whatever you have here remaining here as a subtree, you are going to attach it to the new vertex you're going to have here as a left butterfly rooted at the new vertex. That's what I've done here. So whatever you have here from this, the whole of that is attached here. And this vertex is actually that. Then you proceed to look for the next vertex labeled by 3, which is that. So what you do again, you delete this edge, then just before 6, insert a vertex, and then then insert a vertex, then create an edge between them, then you get that. So it's going to be labeled by 1. So the vertices, so if a vertex was labeled by 3, then it's going to be labeled by 1. That is, if it was labeled by k plus 1, then it is going to be labeled by 1. And if it was labeled by k plus 2, then it's going to be labeled by 2. And you proceed that way. And the one that was labeled by 2k is actually going to be labeled by k. If the root was labeled by 2k, so then the root is going to be labeled by k. And in this case, to complete this, so the one that is remaining here is that label, is this labeled by 4. So just before this vertex 6, you insert a vertex, then connect it to vertex 6 here, and then anything that was to appear here as a left butterfly rooted at this vertex will be inserted here as a left butterfly to the new vertex. So we get this. So you can get the locally oriented tree, locally oriented and crossing tree by orienting the edges. So you'll realize that a vertex that was labeled by k plus 1 become as a source labeled by 1. And the one that was labeled by k plus 2 become a source labeled by 2. And the one that was labeled by k, 2k becomes a source labeled by k. So, and the process can be reversed. So let me introduce also another combinatorial structure, which we'll call weakly labeled trees. So in 2010, again, Pang and Levin in the same paper defined a k-labeled tree as a plain tree whose vertices except the roots receives the labels from this set here. So all the vertices except the root receives the labels in this set. And so we can define a weakly labeled k tree as a k-labeled tree such that the children of the root are labeled by a fixed integer. And each of the vertices except the root receives a label not less than any of its elder siblings. So let's look at this example here. So this vertex here is the root, and these the children of the root are labeled by a fixed integer, in this case 5. Then the children of other vertices receives labels in the set, let's say 1, 2, all the way up to 5, such that the elder children normally receive a lower label than the younger children, less or equals to that. So like this is vertex 1, vertex 2. So this vertex here will not, I mean, if this vertex is 3, then this vertex here could not receive a label 1 or a label 2. And you do that for all the vertices in the tree. So you get a weakly labeled K tree if they are to be labeled with the integers in the set 1, 2, 3 up to K. Okay. So Pang and Lubner therefore showed that the number of weakly labeled K trees on this number of vertices is given by this formula here. And Alois Panholzer and Helmut Brodinger introduced and studied DRE trees, which the vertices receive the labels in this set, but with the property that a label of the child in a rightmost path must not be greater or equals, must be greater or equals to the label of its parent. They obtained a formula counting those trees, and it is given by this formula here. If we set D here to be equals to 2, then we get, that is, they actually called them K-ary trees, the K-binary trees. So if we set K to be equals to 2, then we get a 2-binary tree. Okay, so that's what I've explained. Okay, so here we can compare these two formulas again. If we take D here to be equals to 2, note that you are getting this formula. If D here is equals to 2, then you are getting this formula, meaning that there should be a bijection between the set of weakly labeled K trees on n+1 vertices and the set of 2 binary trees on n vertices, of which the root is labeled by 2. And that is the theorem we want to prove bijectively. So this is what we have here is a 2-binary tree, of which the root is labeled by 5. The root is labeled by 5. And you remember what defined the 2-binary trees, in which if you consider a rightmost child, like a right child, like this tree here is a right child of 1, of this vertex labeled 1 here. So its label must always be greater than that of its parent. Then it becomes a 2-binary tree. And the other, something you can note here is that these labels, if therefore it's to be start 1, 1, then you'll have 3, then 3, then you could proceed that, but you'll not have 3, 1 or 3, 2. They must always be greater than its parent. So we are going to show that this kind of tree here is in bijection with another tree, which is a weakly labeled 5R tree, this one here. So how do you obtain this tree from that? Note that this tree here is to have an extra vertex, because we said the vertices here are n+1, but the vertices here are actually n. So it must receive an extra vertex. So what you do, you start with an extra vertex, which is this. Then the rightmost paths, which are all labeled by 5 here, become the children of that vertex. Then this vertex here, I mean this vertex here, it's the corresponding one is this, but it is connected to this as the first rightmost path. So then these ones become the children of this vertex. So 1, 1, 3, 3 become the children of this vertex. Then this vertex here is connected to this. So its children, its children here become the vertices 1 and 1. So you proceed using the same procedure, then you'll end up with this tree here, which again, you can reverse back to get this tree here. Okay, so you get that bijection. Okay, so if you consider a binary tree T, then we can call a path into a right path if it starts at a left child or the root, and all the vertices on the path are right children, or are the right children. And it's going to be a left path if it starts at a left child, and all the children are left children. So let me just go back to this to explain that. So this 5 here is a right child of that. So, so this path here is going to be a right path because all the children are right children. And this one is also a right child, I mean a right path. This is a left path because all the children are left children. This is also a left path. And a right path that starts at the root will be called a rightmost path. And if the left path starts at the root, then it's called the leftmost path. Like this is the leftmost path, I mean the rightmost path, and that is the leftmost path. And the number of the edges on the path is the length of the path. So a right planted binary tree is going to be a binary tree with a leftmost path of length 0. And if the rightmost path is of length 0, when we call it a left planted binary tree. So a binary tree, which is both right planted and left planted, is said to be, I mean, which is either right planted or left planted, is said to be planted. So we're going to show that there is a bijection between the set of 2 binary trees on n vertices whose roots are labeled by 2 and the set of non-crossing trees on n+1 vertices. Of course, non-crossing trees, the roots are always labeled by 1. So we are going to show that bijection. So we start with let's say this is a 2 binary tree. So we want to get its correspondence non-crossing tree. Then note that the number of the vertices in the non-crossing tree must be n+1. So it's going to be 1 more than that of the binary trees. So we start with that vertex, so as the root. Then these vertices here, which are on the left, I mean the rightmost path, so they become the children of that vertex. That is going to be, you start from here, that is this 2, 2, 2. So the corresponding vertices are this, that we are going to consider this in a clockwise manner. Okay, then if we consider these vertices here, note that they are going to be connected to this vertex here, and the correspondence of this vertex is this on this non-crossing tree is that. So these are going to be connected to this vertex. And if the vertices are going to be the rightmost, the vertices on the right paths are going to be labeled 1, 1, 1 after a certain point, then you start 2, 2, 2, 2, like that. So the 2s are going to be attached as the right butterflies rooted at that particular vertex, and then the 1s are going to be attached as the left butterflies rooted at that particular vertex. You are going to do the attachment. So like this, 1, 1 are going to be attached at this vertex, but as a part of the left butterfly. So you'll have this and that, so they are the left. Then this vertex 2 here is going to be attached to the right as the right butterfly. Then if you consider this vertex here, these vertices here, which are attached to this, so which is attached to that, so they are going to be this 1, 1. So they are going to be attached as the left butterfly. So that, and then you proceed to this vertex here, which is going to be attached to this, which is this vertex here. So they are going to be, since it is labeled by 2, it's going to be attached as a right butterfly. So you get this, the right butterfly. Then you proceed here. So this vertex here was actually that vertex. So they are going to be, it's going to be attached as left butterfly. So it's going to be that. And this process can again be reversed backwards until you end up with the two binary tree with the root labeled by 2. Okay, so Mark Noy from Barcelona showed that the number of non-crossing tree on n vertices such that the degree is d is given by this formula. So note that from our bijection here, if the rightmost path was to have length n, was to have length d, then the degree of this vertex here is supposed to be d. But with the condition that, no, I'm saying if the length of the path here is d, then the degree here is d plus 1. Like this is length 2, but here is degree 3. And then this, the number of vertices here is n plus 1. Meaning that if we replace n here with n plus 1, and we replace d here with, we replace n here with n plus 1, when we should be able to get the number of 2 binary trees on n vertices, whose roots are labeled by 2, such that the rightmost path is of length d minus 1. So we get that formula there. And if we set actually d here to be equals to 1, then we get that there are this number of left planted binary trees, 2 binary trees on n vertices, of which the root is again labeled by 2. And the number of right planted 2 binary trees, root is labeled by 2, is given by this formula. And a simple proof of that, you only need to attach a new vertex to the root of the 2 binary tree as a right, yes, as a right child. Okay, so let's do some conclusions. So in this talk, we have showed that, or we have enumerated k-noncrossing trees according to root degree and forest. So a work that I've done with Professor Stefan Wagner is that we have obtained the number of counting formulas for k-plane trees and k-noncrossing trees according to number of vertices and given labels. Though I didn't present this in this seminar, and it is a work that is there on the archive, and it has been submitted to a journal to be considered for publication. So k non-crossing trees have not been enumerated according to the, and not been enumerated according to the degree of a given vertex, degree sequence, number of leaves, end vertices, descents, boundary edges, ECT. So all of these can be considered. That is, somebody wants to take that up, then it's one point we can collaborate. So we have also presented various bijections here concerning k-plane trees, k-binary trees, weakly labeled k-trees, and locally oriented k-non-crossing trees. Specifically, we obtained a bijection between the sets of two k-plane trees on n vertices and the set of k-non-crossing trees on n vertices. This bijection was actually constructed via k-non-crossing increasing trees. So the question is, can there be a direct bijection between these sets, these two combinatorial structures? So we have also constructed a bijection between the set of k-binary trees, root labeled by k, and the set of weakly labeled k-trees. So the question is, can there be a bijection between the set of weakly labeled k-trees and k-trees, as well as k-non-crossing trees? So these are yet to be established, and we can take that up. So we also obtained new and simpler bijection between the set of two binary trees on n vertices, whose root is labeled by 2, and the set of non-crossing trees on n+1 vertices. So the question is, there could be a bijection between the set of two k binary trees whose root is labeled by 2k, and the set of k non-crossing trees whose root is labeled by k. So this is also something I've not been able to obtain, and it is something we can try out. Okay, so here are some of the references. So what I've presented today is part of this paper here, already published, and some of the results are also in another paper which is under review. And so these are some of the references. So this is my paper with Stefan, what I've just mentioned. It's on there on the archive. And I want to say thank you, asante sana. I want to thank my employer, Maseno University, for the opportunity and for providing me with the conducive environment and the resources to carry out these researches. So thank you very much, and I get to you, Jared. Thank you.
Okay, so thank you very much. And I think it's always our tradition. We can all unmute and thank our Apple speaker this afternoon. Of course, before we will allow some questions. So let's all thank our speaker. Thank you very much, Isaac. I think we have some time for questions, and I will allow some on the floor and some on the chat. Kindly, who want to be the first? Give a comment or a question. Of course, I can see some questions on the chat already, but so maybe we should start from the questions on the chat. And the first question is from Jeff Sanders, and he asks, non-crossing is obviously stronger than planarity since edges lie inside the circle. So can Karatowski's theorem be strengthened for non-crossing trees?
Okay, thank you very much, Professor Jeff Sanders. I actually met Jeff Sanders at EMS, whether Jeff is at EMS. So it is something that can be looked at, because non-crossing trees obviously are plane trees. So the planarity, I think all the results during the planarity should be holding for non-crossing trees, because non-crossing trees are planar graphs. They are drawn on the plane, so they must be planar graphs. Yeah.
Okay.
Then
so maybe do you have any follow-up from the explanation, or it's fine?
So from the next one on the chat.
No, I was asking Jeff if he had a follow-up
Jeff, yeah.
on your answer. Or clarification or anything. Yeah. Oh, he says thanks. Yeah, thanks. So he's yeah, thank you, Isaac. I think he's satisfied. So with that, that helps. And then the second question is, how do I? So Guma Darius is asking, how do I view or get an intuition for cross or non-crossing trees in graph theory? He's a student, or maybe he wants to see how he gets this view also. Yeah.
Okay, so trees can be crossing or non-crossing. So if you look at this graph here, let me look at the last one here. So these ones, the edges are not crossing inside the circle. But if you try to, there could be, let's say this edge here is not here, then you maybe have the edge maybe running from here up to this vertex here. You'll see the edges will be crossing, we'll have one crossing. So crossing trees have been enumerated, yes, but with one crossing. But for k crossing trees where they are crossing at k different points that have not been enumerated, it is something we've been thinking of. Maybe we'll get time to work out something, a problem we had started solving with Professor Stefan Wagner on crossing trees. So we'll be able to deal specifically on the crossing trees, but non-crossing trees, because they are easy to work with, so people go for non-crossing trees, and the results there is also very interesting. So that's maybe people study them more than the crossing trees. Yeah.
Darius, you have any follow-up to the explanation? Maybe something you need more clarity? Oh, it seems to be fine. So another question on the floor. So thank you, Isaac, again. Do I have another one on the chat? Yes. So Ahmad Babikar asks, thank you very much for the presentation. And he wants to know, how do you label the vertices?
Okay.
Is it arbitrary? Like, do you need to compensate for the labeling?
Yes, it is arbitrary.
Yeah.
Only that it is arbitrary. Only that the conditions have to be satisfied. Like I plus j should be less or equals to k plus 1 if it is an ascent for the non-crossing trees. But for the plain trees, that the ascent condition does not hold. So it is arbitrary.
Great. Thank you. So I think thank you very much. I think today was an exciting talk. That was important. And we had a lot of actually viewers on our live stream on YouTube. I think many of them, lots of congratulations message. And I think this is something we should do all the time. And thank you for coming. And it was really an exciting talk, very interesting. And it was those talks you could follow until the proof starts, and then you start seeing the most exciting generating functions and other interesting. It was a talk which really was very nice and well presented. So thank you very much, and thank you everyone for this week, because you made it happen. You are always making it happen. See you next week for the next talk. So thank you very much, everyone.
Thank you very much, everyone. Thank you.
Thank you. Thank you so much.